Alright, so let's do the part 3 of the lecture 4. I'm going to talk about the precipitation reactions. The precipitation reaction have a generic form of the molecule AB reacting with the CD, and they swap the partners in a way. So the positive side, these are A and C is the positive side, and then B and D is the negative side. So they swap the partners, A combining with D and B combining with C to create the AD, which could be solid or aqueous, or the CB, which could be solid or aqueous. So example of this generic form is that you have mercuries with the NO3 reacting with the Ki, and now you see that Hg2, the left hand side of the molecule, combining with I, two of those, to become a solid, and then the K, the positive side, is gonna swap and combine with the NO3 so you're gonna form the two of those KNO3, which is aqueous phase. So the key thing is that you are going to swap the positive side and negative side of the reactant. So A is gonna combine with D, and then B is gonna stick with the C right here, and then find out that which one of these things becomes solid. So that's the generic form of the precipitation reactions. The amount of the precipitation is called the solubilities. The solubility is the maximum amount of solid that can be dissolved in a given amount of solvent at specific temperatures. I don't think we're gonna deal with these things in the general chemistry 1 in any of the universities. So that's the general chemistry 2 topic. So the solubility, the only thing at this moment, the only thing that's important is solubility depends on the temperature. So if the temperature of the solvent solution changes, then or the solvent changes, then the solute, the amount of solute that can be dissolved is going to change. Now, of course, that this could be readily see in the kitchens, right? That if you boil the water and then you try to dissolve salt, then you can dissolve a lot more if the water is hot, right? So the temperature determines the amount of the solute that can be dissolved. And some definitions, the hydration is a process that for example, like in this particular case, you have a solid here, right? And that solid, maybe NaCl, then that can actually dissolve into the water, and then when it dissolved, it actually sort of create a caged-like structures. So the minus ion is caged by the positive side of the water molecules, and then the positive ions may be surrounded by the negative side of the water molecules. Those are called hydrations. The hydration literally means that you have some charged particle that's surrounded by the water molecule. And that's usually what happens. So before I go into the super important table, what I want you to know is that anytime that you have a solubility reactions, you have to figure out, is this aqueous or is this solid? So for that, you have to do it like 4 times for that and that, right? So all 4 of these guys has to be identified as solid or aqueous phase. So how do I do that? So anytime that you have a molecule of the 2 things combined, then you can use this table to figure out whether this is soluble or not. So the first table, this one right here, is a solubility table, the water soluble or the soluble compound table. So anything that's shown here is water soluble, and exceptions are given here. So according to this one, the lithium combined with anything, for example like OH, is water soluble. There is no exceptions. The Na plus, that's water soluble, or the K plus is water soluble, no matter what's being connected or combined. Rb plus and Cs plus and ammonia 2, all of those are no exceptions. Everything is going to be water soluble. So the example could be maybe potassium Cl. Those are water soluble because K combined with anything is water soluble. Okay. Now, some of these guys have the exceptions. For example, like HBr is water soluble, but AgBr is a solid. Anytime that you have a water soluble stuff, you have to put the AQ on it. So how did I know that this is water insoluble? This is insoluble. Insoluble. Because anything that's combined with Br is water soluble, except when it combined with Ag or Hg2 or Pb2. So AgBr actually belongs to this exception because it's exception to the soluble compound table, it is insoluble. I hope that makes sense. Let me do the one more stuff here. Maybe the H2SO4. Where's my pen? There you go. H2SO4. SO4 2 minus is always water soluble except when they combine with the stuff that's listed here. H is not in here, so this has to be soluble. That means that I'm gonna have to put AQ on it here. If I have the Ag2 SO4, then that compound right here is water insoluble because anything that's paired with SO4 2 minus is water soluble except these guys, right? So Ag is actually in here. So Ag2SO4 is insoluble. Now, you may be wondering why I have this Ag2 here, or the H2. The Ag is a singly charged stuff, right? Ag plus, right? And SO4, which is 2 minus, right? So look at this charge stuff here. plus and 2 minus. You need to have 2 plus to cancel out this 2 minus here. So for that, you need 2 Ag plus, 2 Ag plus to neutralize this SO4 2 minus. So that's why I have 2 here. Same goes with the H2SO4. SO4 2 minus, H plus, you need 2 of those H plus to cancel out the charges to make the neutral, right? So I hope that makes sense. Alright, so let's do the next table. This one right here is an insoluble compound table, which means that anything that combined with CO3 CO3 2 minus will be insoluble no matter whatever the things that's combined, except when they paired up with these guys. So H2CO3, remind you that you're gonna need 2 of those H, right, to counterbalance this 2 minus. That is water insoluble, right, because H is not in here. So anything that combined with these guys are water insoluble, except when they're combined with these guys. So that means H2CO3 is actually a solid. But when they're combined with lithium, for example, you still need 2 of those guys. Now that the 2 charge is going to cancel. That one right there is water soluble. So that's why you need to actually put AQ here. Now, similarly, if I actually have the OH, what's a good one? AgOH is water insoluble because OH is generally water insoluble except these guys, right? Combined when they make the compound that contains these guys. So the Ag is not on this list, so that's solid. But when you actually combine with a lithium OH, that is AQ. Oops, AQ. It's water soluble. So each time that you actually make the solubility reaction formulas, all 4 of those chemicals, you need to check whether that is solid or the AQ. So let's check if you can actually get these things. BaNO32. So let's check the Ba. NO32, maybe the NO32. Yeah, right here. I find NO3. NO3 combined with anything is water soluble. So that has to be water soluble, right? Alright, what about AgI? I find I here, but I combined with anything is water soluble except when they combined with Ag plus. So that one is in exceptions, which means that this one is solid, water insoluble, right? And then the MgOH2, I'm looking at OH minus. OH minus, when they combined with these guys, when they combined with anything which is gonna be water insoluble, exception is this one, right? but Mg is not on this list, so that means that it's going to be solid. So water insoluble here. I hope that one is clear now. Alright, so let's do the molecular equations. So let's just think about this one. Na2SO4. Now you're going to use this table, Na2SO4. That's water soluble, right? That's going to be AQ. And then BaOH2, that's water soluble, right? So that's also AQ. Now Ba has a form of 2 plus, right? And then OH minus times 2, right? So these are balanced. And then also Na plus, you have 2 of those, and then SO4 2 minus, right? So the minus stuff is gonna combine with this guy, right? So BaSO4, so check the BaSO4. What's a good one here? Yeah, the SO4 2 minus is water soluble except when they combined with the Ba. So that's water insoluble. So I have to put solid in here. That's solid. And then the NaOH, that's water soluble, right? Na is water soluble no matter what. So that's AQ. So these are called molecular equations. Alright. Then ionic equations, you're going to separate everything. When they are denoted as AQ, you are going to separate every one of those guys. So Na2SO4 becomes that, BaOH2 becomes that, and then NaOH becomes this. Now you want to substitute these guys, right? When you do that, this becomes this one right here. That's called ionic equations. See this one, like Na2SO4 is actually these guys, and then BaOH2 is those guys, right? And then NaOH is those guys, right? You have 2 of those, right? And then BaSO4, when it's solid, you don't do anything, just keep it like this. Now I'm gonna cancel the stuff that's happening on both sides. That's, you don't need that one. What else is there? You don't need that one either, right? Now that's pretty much it. Then what happens is that if you combine the rest of those, you get these guys, and that's called net ionic equations. I hope you do actually see the similarities between the acid-base reactions, because they are pretty much the same stuff here. The procedure is pretty much the same. So here's the procedures. It's the same stuff. You're gonna have to use a table. That means that whether you are going to well, actually, let me just think. I will give you the table for the exam, but for the final exam, you're gonna have to remember this one, okay? For the midterm exam, I will give you this table, okay? So you don't have to memorize that one, but you do have to memorize these guys when it comes to the final. And you can probably do these things when you actually have a time. So stop the videos and then you can probably check whether you actually get this or not. I think that's probably about it. The final net ionic equation should look like this. I think that's good enough.